So welcome everybody to our monthly longer form tech chat. This month we have Ed Bennett, who's going to be talking about developing and using a cluster of Raspberry Pis for outreach. So when you're ready, Ed.
Thank you, Mark. So this talk is very heavily based on one I gave at the RSE Conference last year. So if you were there for that, much of the content will be familiar. At the end, I've added a little update on our more recent progress. Had I had more time, I would have added more slides about that, but unfortunately, we ran short of time. So it's important to say going in, this is not all my work. This has been the work of a lot of people, and they are listed on the screen there. So thank you to Mark, thank you to Chenna, who isn't here today. Thank you to Michele, thank you to Jano, who has moved on to Finland, for everyone's contributions. So for those of you who might not be familiar, there's a brief introduction to what Supercomputing Wales is. So this was a £15 million investment across 6 years, including £9 million from the European Union through Welsh Government, and then £6 million from the 4 Welsh universities, Aberystwyth, Bangor, Cardiff and Swansea, with the objective of increasing research income to Welsh universities. This was the successor to the HPC Wales project, whose objective was to increase HPC usage among small, medium enterprises. So this has given us 2 HPC hardware hubs. It's given us the Hawk cluster in Cardiff, the Sunbird cluster in Swansea, as well as some data analytics platforms and data storage attached to these devices. So the motivation for this is articles like this that came out of the HPC Wales project. So HPC Wales supposedly spent £40 million claiming to create 400 jobs, only created 170, and this is £200,000 spent per job, which is an unreasonable amount. So this was a reporter for Wales Online, who, when you start name searching, you find a lot of articles critical of Welsh Government spending, but it's how can we try and avoid this kind of messaging around the Supercomputing Wales project? Because this was messaging from the HPC Wales project claiming it to be a waste of money, whereas we want to try and avoid that for Supercomputing Wales, so we want to try and shape the message a bit more, try and communicate to members of the public how Supercomputing Wales is benefiting Welsh research and Wales as a whole, how it all works, what the point of it is. So that was kind of what we were setting out to do. So the first thing we want to do was to illustrate the principles of high-performance computing to a non-technical audience. So most people in Wales don't know what a high-performance computer is. They've probably heard of a supercomputer, but they've never used one. They probably never will use one. So just getting a feel for the technical aspects of how it works without going into too much detail. Second is to demonstrate some of the computational science done using Supercomputing Wales facilities. So we do a lot of cutting-edge science using the machines in Swansea and Cardiff, and conveying to members of the public what that is and why they should care about it and why it's a good use of public money. And then finally, the third point was to provide some kind of a focal point for discussions around HPC. So around these 2 topics, discussions naturally start and conversations happen, and people feel like they're more engaged with the process and more engaged with what's going on in Welsh universities and in academia and in science in general. So that's kind of what we were setting out to be able to do with this. And to do this, we decided, based on what we'd seen successfully done at other HPC centres, a Raspberry Pi cluster mimicking the style of a supercomputer, but built out of much smaller computational units and at significantly lower cost, would be a good way to demonstrate this. So the initial design thoughts we had, this was based strongly on machines like the WeArchie that's been built by EPCC. So we're not claiming to be the first to do this, we're not claiming to be best to do this either, but we did what we could based on the resources we had available, and this is what we were initially setting out to do. We're going to try and have Raspberry Pi 3B pluses because there isn't significant saving to going to earlier generations, and this was the newest generation when we were setting out to do this. Having 16 compute nodes and then 2 login or service nodes to do visualization and management and that kind of thing. Had some kind of a plastic casing with a handle that you can carry around, could easily put in the boot of a car. Have these in some kind of stacked configuration, so it's relatively compact, maybe like a tall briefcase kind of size. Then using extension cables from the login node to the outer casing, so you don't have to be plugging things into the Pis all the time. You have the Pis quite isolated inside the plastic case. Then have some small 24-port switch in the base of the machine so that you could then have all 18 nodes plugged into it, plus a couple of external computers. Then use some kind of a 300-watt 5-volt transformer, because you don't necessarily want to have massive power bricks for every one. So being able to wire them in directly seems to avoid waste, avoid having lots of separate transformers, and that could then be concealed in the base so that you have a nice clean design on the top. And then we're thinking have 2 SD cards for the login nodes. So boot the compute nodes over the network from one of the login nodes, but then be able to run slightly different software stacks on the 2 login nodes if necessary. So this is what we thought going in. You'll see as we go through how much of this we achieved and how much of this we had to change on the fly. So for power, I already alluded to this. That is not a very good solution for powering a relatively compact cluster that you want to fit on the boot of a car. You need to have more than 18 British standard power sockets available. Even with extension cables, this would be incredibly space consuming in the base, so we decided that was a no-go. Also, cost-wise, each of those costs £5, so then you're looking at almost £100 just for what should be significantly less, you'd hope. So next option we thought of was something like this, some kind of industrial multi-USB power supply. If I bought this today, then this would be the way to do it. These have come down in price a lot. Unfortunately, when we were looking at this back in 2018, when we were starting the procurement for this, these were costing over £100 for this many ports, which was more than we were willing to pay for this and more than what the alternatives would be. So we rejected this option as well. So our first effort was with this. This is a relatively inexpensive voltage source that will deliver 5 volts. It will deliver up to 300 watts. So in principle, you can wire in 18 Raspberry Pis to those terminals. You don't want to wire them directly because while you can power the device directly on the pins, it doesn't provide any protection from over or under voltage. So then it can quite easily damage the chips on the Pi. So what we did instead was try and wire in some micro USB cables to this so that you go via the fuse on the Pi so that it's then protected against any overvoltage. The problem we had with this is that as soon as we plugged a micro USB cable into it and into a Pi, the thing went pop and didn't work anymore. So deciding that our electronics skills were not quite as good as we had hoped they'd be and not quite up to the task of getting this working, we switched to an alternative solution which was slightly more expensive, but was a good compromise of price versus being compact. And that was these RAV Power USB power supplies. So each of these has 6 ports on, so between 3 of them we can power 18 Pis. They cost about £20 each, so it was less than buying the individual AC adapters and a lot more compact as well. And they could still be concealed relatively smallly in the base of the machine. So, solution to our power problems. So, next thing was how we're going to network these together. So initially we wanted a small switch that would be compact enough to put in the base of the machine. The College of Science had a spare switch available of the right size. We plugged this in, we tested it with 2 machines, they were able to talk to each other, so we had a working switch. Until we'd spent a significant amount of time trying to debug why network booting wasn't working. We were able to boot a single Pi off the network. As soon as we had more than 1 Pi, then the entire thing fell apart. It turns out this switch has a fault, such that when you plug more than 2 devices into it, the entire thing effectively goes haywire. All the lights start flashing, and it starts sending garbage network traffic, and nothing works anymore. So after eliminating the faulty switch, we found instead this surplus switch from HPC Wales, which is no longer under a service contract, so it can't be used in production anymore, but it's a perfectly functional high-performance switch. The problems it has 48 ports, which means we've got a lot of expandability. It's not really what we wanted, though. It is twice the size of the previous switch, if not bigger. It's incredibly heavy, and it's also incredibly loud. So we're kind of limited in the circumstances we can use it. We can't really run it in a quiet room as a demonstration of the cluster, which is something we'd be looking to replace if and when we find budget for it. But we do have a working switch. That did then mean that we needed to change the case design, because this won't fit in the base. Well, it wouldn't fit in a compact base. So instead, what we did was we laid out the boards in a flat configuration such that it fits neatly on top of that switch. Another problem with that switch, of course, is that it kind of looks similar in size, shape to a compute node or to a server. So it might give the impression to visitors that, just a second, are you sure you're not doing all the computation on that thing there that looks like a computer, rather than this thing here that looks a bit weird. So the way we deal with this in practice is to put the switch under the desk, out of sight, out of mind, out of the way, and then just have the network cables visibly going underneath the table to get to it. But this is the case design we went for. You can see the number of compute nodes has gone down. We now have 16 nodes total, because two of the Raspberry Pis died during the production process. So we now have 16 nodes total, 14 compute nodes, and then 2 management nodes. So that's the top-down view. You can also see a side-on view. So you can see there's a top layer that has the Pis and the network cabling, and then concealed underneath in the base we've got the USB power supplies. These are then that's all separated with these standoffs with I think it's a standard 3mm thread that those are using. So a brief aside on mounting a Pi, because I learned stuff about this. I found it quite fun, and hopefully some of you, either in the audience or online, might find it interesting as well. So here is a Raspberry Pi, and you can see it has 4 holes. However, those are not designed for mounting. You read the material online about the Pi, and it says whenever anyone on the Raspberry Pi forums mentions the mounting holes, you get an angry reply. Those are not mounting holes. Those are not holes designed for mounting. They're for propping the Pi up in the manufacturing process so that it can be tested. And apart from that, they're not for mounting, they're just holes. It's like, okay. That means that you have to be quite careful if you are going to use them for mounting, because the Raspberry Pi, being such a compact device, is quite a complicated circuit board. I think it's 6 layers thick, which means it's quite vulnerable to being compressed. If you compress it, then you can destroy the circuitry and it no longer works. So you've got to be quite careful when you mount, well, if and when you mount a Pi using this, that you don't over-tighten your screws, because otherwise you kill the Pi, which is bad. However, you can, I've already said you can mount it. The other problem you have is that they're slightly smaller than your standard 3mm case screw. So you can use 2.5mm screws with them. However, 2.5mm screws are non-standard and so are significantly more expensive than 3mm screws to buy. The other thing you can do is you can get a drill and a 3mm drill bit and drill out those holes. Because you can see around the edge of them there's quite a lot of slack space on the board there to allow for tolerances when producing them. And so, it will tolerate being very carefully and gently drilled out with a 3mm drill bit. That then lets you use standard 3mm case screws. So Then you can use a 3mm thread tap. If you've never used a thread tap, I recommend trying it because it's really satisfying to put in the correct screw thread into the side of your hole, and then the 3mm case screw mates into it perfectly. And it's all very pleasant. And there is a picture of a detail shot of it actually being mounted. You can see the standoff there. That's a standard 3mm case standoff, and then a standard 3mm case screw. And I think it was something like maybe £10 for 5,000 of those screws. So we have a lot of surplus case screws, but it was cheaper than buying fewer of them. Quick bill of materials, or at least set of costs. So the main expense was buying 18 Raspberry Pi 3D Pluses. We paid over £500 for that total. And then the total cost came out to about £900. I say 3 vinyl stickers there because you couldn't buy fewer than 3. There was a minimum order, so we've ended up with 2 surplus Supercomputing Wales vinyl stickers that we can use if we build future clusters, perhaps. So that's the hardware side of things. Moving on to the software. So I'm going to talk first about the version 1 software stack that we demoed in 2018. And at the end, I'll go on to the version 2 software stack that wasn't ready in time for the first time I gave this talk. So the concept we had, we want to demonstrate some of the research that's being done in Swansea using the Supercomputing Wales facilities, and do that in a way that's accessible to a member of the general public. So one of the big research areas in Swansea is computational fluid dynamics and finite element methods for that. So we thought if we could demonstrate concepts of computational fluid dynamics to a member of the general public, they might better appreciate how supercomputing is applied in Swansea. And then we could also use that problem to talk about some of the challenges of getting that working on a supercomputer. So the concept we have is visitors stand in front of a Kinect camera and strike some kind of a pose. Then we generate a mesh from their outline. We do this in 2D because we're doing this on Raspberry Pis. We don't have enough computational power to do a 3D simulation. And then from this, we do some kind of CFD, and from this we get a colour map of the airflow over them, assuming some wind direction. And we overlay that onto the image. So from that we can calculate some measure of drag, which we can use to put together a leaderboard of who is the most aerodynamic person who's visited us that day, which we were told by the Swansea Science Festival, people around that works quite well in terms of generating engagement and in terms of keeping people excited about things, is being able to compete against other people, possibly having a prize at the end of the day, although we didn't end up doing that. And then also producing a postcard so that everyone who comes to the stand has something to take away with them, with their picture on it, and then their airflow as well, and then the requisite Supercomputing Wales and Welsh Government logos, so that they know they can associate our brand with something positive they've had to take away, which is the opposite of what the news story that we showed at the start of bad press. So hopefully this will meet our aims. So looking at the implementation of the software, how do we do it? So for the front end, we used PySide 2. Then we used the lib-freenect for integrating with the Kinect camera. We use the Kinect camera to be able to get a depth map, so it makes it a lot easier to do outline detection to find where the outline of the person is, compared to doing that with computer vision. We use Elmer, which is a CFD library, to do the CFD component of it. Then we use VTK for visualization, for rendering the output. Then initially, for version 1, we used a bespoke bare-bones queue manager that we built on top of Fabric, which is a library for communication between nodes in Python. And then for generation of PDFs for the postcards, we used a library called Report Lab, which I'd used previously and was quite familiar with, so was able to implement relatively simply. So some of the challenges we had. The first one is the direct solver in Elmer, as far as we could tell, didn't support ARM. So running on a Raspberry Pi, we need ARM support. So we had to use an iterative solver. Problem we get then is that some contours would fail to converge. So we'd sit there waiting as the spinning wheel of death told us that nothing was happening. So what we ended up having to do there, at least in the initial implementation, was start simplifying contours so that if they didn't converge in reasonable time, then we round them off and try again so that they do finish in reasonable time. The only problem with this approach is it tends to create blob monsters. So you can see that the image on the right shows the mesh that we were using, and how the image on the right is not really the shape that Mark has in real life. So it's a little bit unfortunate. So we prefer to use a direct solver and sacrifice solution quality for finishing in reasonable time and having the right shape. So next issue we had was trying to run multiple video streams, because we were running two or three screens off the front end. This had multiple different streams of animation because we were showing both the camera view and the depth map, and then then also the results were animated as well. So the Pi is fine for displaying one video stream. You can happily watch a video on that. But once you start trying to display multiple video streams, then you get really, really poor frame rate issues. And so what we did instead, again in the initial implementation, was to swap out the Raspberry Pi for Mac Pro. Of course, the computation was still being done on the Raspberry Pis. Everything meaningful was being done on the Pis. The only thing we were doing on the Mac Pro was visualizing the results, because the Pi didn't have enough video performance. We kept the Mac Pro under the desk to avoid questions about this, but it served us well for the first few demos we ran with this. So the next problem we had was that because we're using a Kinect camera, the Kinect camera has two cameras in it. It's got a optical camera for actually getting the picture, and it's got an infrared camera for measuring distance. And these are separated by some finite distance, maybe about 15 centimeters or so. So you get some kind of a parallax effect, where you've got two cameras that see the subject at slightly different angles, which means then when you're trying to calculate the contour and subtract that from the image, then they're misaligned. So what we were able to do here is we used OpenCV to implement some kind of affine transformation to apply that to the outline to shift it to such a point where then it was correctly aligned with the optical image. And then I think the final problem we had software-wise was that we don't know how far away the visitor will stand. So initially we thought we'd have a cutoff depth, and then anything that appears in front of that cutoff will be a person, then anything that's behind it is background. But the problem we have is that the person might stand in front of some elements and behind other elements of the frame, so we have trouble separating the forest from the trees. So the way we dealt with this, so we don't know how far that distance is, what we do instead is remove the visitor from the frame, then take a capture, and then use that as a background image, and then do background subtraction to find where the person is. And that worked quite well, combined with the way we calculate the contour, which was by finding the biggest object. That meant any noise from imperfect background subtraction didn't really matter, because the noise will be significantly smaller than the size of the person, so the person will end up being the largest contour that gets meshed and has some simulation done. So next up, some footage of this in action. So here we got a video of a typical interaction. This is in a test office environment rather than being anything in production. But Mark there has walked in front of the frame. We've taken a capture to get Mark's outline. Mark can then walk forwards and backwards, and we can talk about how the depth map works. It gives another topic of conversation. People were really interested in this when we ran it in practice, is that, oh wow, that's a depth map? That's really cool. even though Kinect has been out for, I think, is it over 10 years now, maybe even 15 years, Kinect has been around, but nobody, well, at least games on Xbox don't really show you the raw data from that. So people are still impressed by what it can do. Then we submit that to a queue, and while the image is being processed, while the CFD is being done, we will show them this queue view and talk about how the work is being distributed among the different nodes, and then how multiple sets of nodes can do different tasks at the same time. So we've got 4 nodes doing one person's image, 4 nodes doing another person's image, 4 nodes waiting for someone else's image to arrive to be done. So they can get an idea of both work sharing and then also workload management, about how we can fit multiple different pieces of research on the same supercomputer at once. Which is something that isn't frequently discussed when you talk about the power of supercomputers, so I thought it was an interesting thing to add. Then we get an outline, we get an animation of it, so you can see how the iterative solver converges and the final stable airflow over, in this case, Mark. And then you also show this the mesh with then the same data overlaid in a slightly different way. And from that, we can generate a postcard that looks something like this. You can see, compared with the previous image, this was mirrored because people are used to looking at themselves and seeing it mirrored, but then in the postcard form, it reverts back to being the correct way round. So then the banner in the background has the text the right way round and things, and it's got all the branding on, showing who's paid for it and who they should support in their next funding application. So like I said, the first place we demoed this was at Swansea Science Festival 2018. Because it was quite a chaotic event and we had very little time because we were preparing things relatively last minute, we didn't get any good photos from this, but this is a photo of what the event was like. We had really good engagement from our audience. They really, really enjoyed coming to interact with us and everything I just talked about. And yeah, we were busy all I think both days of the Science Festival. We were almost constantly talking to people, which was really great. So that was the kind of event that we developed this for. Another event that we have demonstrated this at is the Wales Programme Monitoring Group, which is a group of bigwigs in Welsh Government who look at how the programmes funded by Welsh Government are doing, have some very dry conversations, but we were invited to be on a stall demonstrating some of the... They had an entire set of stalls from various projects to talk about what work we were doing. And so we took this along just as a talking piece. We didn't set up the demo because this wasn't a group of children and science enthusiasts coming to have a hands-on experience. This was a much drier event, but we had it there just as a prop to be able to talk about how high-performance computing works, try and help some of the bureaucrats who are making these decisions understand better how the underlying technology works so that they're better informed next time they need to make a decision about it, which is hopefully useful for them. Then we going on to new stuff, which is, again, going to be shorter than I'd like because I haven't had time to put together slides on it. We once again demoed this at the Science Festival 2019, so a few months ago. As part of this, we redeveloped the software stack. We tried to iron out a lot of the kinks we'd had previously. So previously we were relying on this Mac Pro because the video streams were too much. We were able to split out some of the video streams and split out some of the views so that then we didn't require the power of Mac Pro. Instead, we were able to use a Microsoft Surface for controlling the machine. Then we were able to use more Microsoft Surfaces because we have a lot of Microsoft Surfaces in the office, able to use those for displaying the results. So we displayed the results now as HTML, viewed over HTTP, so you can connect to a web server that's running on the login node of the cluster, and you get served up the results, and then you, from the client that's handling the camera, that then pushes requests to a server that's running on the Pi. So there's much better separation of client and server. It's a lot easier to reason about what the data flow is. Whereas previously, everything was kind of very tightly coupled, directly interlinked, and managing state of remote machines and stuff, whereas this is a lot more sane. We also ditched the proprietary, very basic queue manager we were using and switched to using Slurm. So now the cluster does use Slurm, which is exactly the same cluster management tool that we use on the Supercomputing Wales cluster. So that's another talking point for talking to people. This actually runs the same queue manager as we run on some of the world's largest supercomputers, which is kind of fun. We have now also open sourced this. This is available on GitHub. I don't have a link in the talk. If you go to the YouTube page after the fact or to the seminar schedule, I'll put a link to the software there so that you can find it. So based on the fact that we were able to make all of these improvements and have a much more stable experience for the second time we ran this at the Science Festival, the things that we've learnt are that there are two important things when you're embarking on a project like this that it's very easy to underestimate: time and money. And while to some extent these are fungible, time is money and all that, they are both really important. So we started this project in, I think, late July or August 2018, and the Science Festival was in November. So this gave us 3 or 4 months to do the prep, but we underestimated the scope, and so by the time we were actually seriously developing, we were getting far too close to the Science Festival, and we ended up doing... We were writing software while visitors were walking past the stand because it was not ready, because we had not allowed enough time. So that's a lesson I've learnt, is that when you're managing projects like this, you want to have as aggressive timelines as possible, get things as ready as far in advance as you can, because you will always encounter problems and you will always have delays. And the more time you can build in to allow for those, the better. Similarly, on the money side, we had a fixed budget, and when we put in the request to Welsh Government to be able to spend some of the Supercomputing Wales budget on producing this, we estimated it would cost around £1,000. And we were right, we could build it for around £1,000. However, as we saw, we had to replace some components, and some components we had to get scrounged for free because we didn't have enough budget to buy the right component for the job. So had we requested maybe 50% more, it's £500. In the grand scheme of a £15 million project, it's a small amount of money. So had we requested that bit extra, we would have had some buffer to be able to buy the right equipment, replace parts that had broken, and make sure that we got a better piece of hardware in the end. The hardware we've got is great, it's a great demo tool, and it does a great job, but there are some niggling corners that would have been nice to fix had we had some more budget. So had we allowed maybe 50% more time and 50% more budget, it would have maybe been 100% better than it ended up being for the first time we ran it through. We've now had the time, we've been able to polish it off, and I think we've now got a really great solution that we can use for future outreach events. It really does spark really great conversations around HPC and also around some of the HPC-based research that happens in Swansea. So I think it's been a real success in that regard. People seem to really enjoy it. If you haven't built a Raspberry Pi cluster and used it for outreach before, I'd recommend you try it too. It's quite fun. And that's all I had to say. So thank you very much, and I'll take questions if anyone has any. Let's have a chat. Thank you.
Well, where did you get the images from? Are they
Which ones?
actual, the cat videos, are they actually from the Pi, or are they sort of simulated frame rate?
That's simulated frame rate. That is... the video is a video I happen to have on my phone of a cat rolling around at the top of my drive, and then it was quite tricky because if I go back, where's that gone? There. Because you want it to have enough motion that it's clear when the frame rate goes down. You also want it to have sufficiently little motion that when you loop it, it doesn't cause people to vomit in the audience. The most of the images I had a problem with would really create flashing image problems if I did it. This is the only image I found was relatively stable. As a bonus, it's also of a very fluffy cat who lives a few doors down from us. He's like 20 years old now, I think, so it's kind of an elderly cat, but still very friendly and very fluffy.
And very active.
Well, was when this was taken. I've not seen him in the last year, so I hope he's okay. Yeah. But yeah, cat videos. Also, I like having an excuse to show cat videos in a talk. So
It's 20 years old now, and you speed up. It seems too likely to be 20 years old.
I mean, when the video was taken, I think he was maybe 15 or 17. But he's just a really friendly, really happy, still quite active cat.
Are there any plans to remove the circuit, to move more processing onto the Raspberry Pis?
It's a good question. In principle, I think the problem you get is power. So we've got 2 login nodes on the Pi. Sorry, two login nodes that are Pis on the cluster. One of them is handling NFS and net booting, so that has to be powered externally from the nice USB power supplies that I talked about, because it needs to boot up first. That then means that it's always a little bit starved of power, so you can't do very much on that. So we have one Pi for doing all of the key management, all of the file management, then serving up the web server, and also managing requests. So getting that to handle the Connect as well, I think you might start to hit the power limit of the Pi, or at least you wouldn't get a very nice frame rate out of it potentially. It would be nice if that ran for the Pi as well. In principle, you could do the results displays on the Pi as well. That could still run, just run a browser pointing at localhost. That potentially wouldn't be too much load. Although that's that's actually displaying the results in JavaScript, isn't it? So that's probably going to be more load than you want on the Pi. It's also doing a lot of heavy lifting. So if we wanted to do more on Pis, we need to expand the cluster slightly, I think.
Would it make sense to use some of the Pis that are now used for compute or that?
That's an option. So we do have, because we tend to divide problems up into 4-node blocks, and currently we have a non-multiple of 4 compute nodes, so we could take 2 compute nodes out of circulation and use those for showing results and showing the viewfinder. I quite like the touchscreen aspect of the results, because you can visitors can just pick up the surface and swipe through the results and tap on their image, tap on other people's images. It's quite nice and interactive, whereas with a Pi you then have to have a mouse and interact with it that way. For the viewfinder, it would probably be nice to do that on the Pis, make it remove the extra computer that looks like it might be doing some work. If we could attach a wireless access point to the switch, then we could actually use some kind of tablet that is obviously underpowered rather than a powerful Microsoft Surface, which would be good. But we need to procure that then. So. But yes, that is an option that we should probably think about. I guess the ratio of service nodes to compute nodes then is quite high, but you can always use that as a talking point. As you scale up your number of compute nodes, you don't need to scale up your service nodes as quickly. So.
Are there any future plans for?
That's a very good question. We have sent in we have sent in the paperwork to be at the Super Science Swansea event in March 2020. If you are watching this video before March 2020, we haven't been approved yet, but you will probably be able to come and see us there if you want to see the cluster in action.
Right, so if there are no further questions, let's thank Ed once again for speaking. Thank you very much, Ed.
Well, thank you.